Recording in progress. So we are now in chapter 10. We're gonna continue our video. So we are now in the angular momentum. So this is video number 5, if I'm not mistaken. So what is angular momentum, by the way? Okay. Uh, so let's talk about the momentum. Okay, and so in every rotational quantity we have the encountered in chapter 9 and 10 is the analog of the sum quantity of the translational motion of a particle. So the analog momentum of a particle is the angular momentum. Okay, the vector quantity denoted as L. Okay, so if you remember the momentum, which is the P, okay, the angular momentum, the analog of that is L. Okay, in relationship to the momentum P, okay, which we often call as linear momentum, for clarity, it's like the same as the relationship of, of, of torque force. Okay, di ba? Ang torque is just equal to R cross F. So for a particle with constant mass, velocity v, the momentum is equal to mv, and the position vector r relative to the origin O at an inertial frame of reference. Okay. And here we define the angular momentum. L is just equal to R cross P. So R cross P. Okay. Since R is equal to MV, P is equal to MV, so we have R cross MV is just equal to, so here we can see that the direction of our angular momentum is along the z-axis perpendicular to the xy plane. So if you do the right hand rule, so R cross V, R cross P, so our angular momentum of the particle is along the, okay, since so R cross P, so we have here this is equal to the definition mv r sine of phi, where phi is equal to the angle between r and momentum p. So we have, so here this is equal to the lever arm, L is equal to r sine theta. So the linear momentum is equal to mvl. Okay. Also, okay, if you do the rate of change of the angular momentum, so for example, we have, let's put it here, uh, dl over dt. So this is equal to the d over dt of r cross mv. Okay, so this is actually using the chain rule, okay, the product rule. So this is actually the dr over dt cross mv. Okay, and is this the product rule plus r cross m dv over dt, r cross dv over dt. So here dr over dt is just equal to v cross mv plus we have r cross m, r cross m times the acceleration. Okay. Okay. So here, from this equation, so the first is, if you that so the dot product of this one is 0 because they are parallel. Okay, so the dot product of that is 0. So you are left that the dl over the rate of change of our angular momentum is just equal to r cross ma r cross f, which is equal to the torque. Okay. So here, the rate of change of our angular momentum of particle equals to the torque of the net force acting on it. So that is the relationship of the torque and the angular momentum. Okay. If you consider a rigid body to find the total angular momentum of a rigid body rotating with angular speed, okay, first consider a thin slice of an object. Each particle in the slice with mass mi has angular momentum L is equal to mr over omega. So how did we get this one? So here, if you remember, the angular momentum L is equal to m v r sine of v. Okay. So here, uh, v is equal to m. V is just equal to, for example, mi. Okay, mi. So in mi, ri, okay, vi. Okay. V is just equal to ri omega. Okay, ri omega times ri. Okay, ri. Okay. So sine phi. So the since for sine, since the perpendicular, since the r and vi are 90 degrees perpendicular, so sine of 90 is just equal to 1. So we have m I ri squared omega. Okay. So here, your linear momentum of a rigid body, uh, so Li, this is actually Li. Okay. So if you sum it all, so let's note that L is equal to the sum of Li is equal to uh, the summation of Mi Ri squared omega is equal to I omega. Okay, so we have here the definition of the angular momentum of a rigid body. L is equal to I times omega. Okay. So the I is the moment of inertia times, okay. In vector form, okay, L is equal to I times angular velocity. Okay, this is the rigid, for a rigid body around a symmetry axis. Okay. So again, for any system of particles, okay, the net torque is equal to dl over dt. Okay, let's try to apply this one. So this is the for a rigid body for any system of particles. So this is our formula. So we have here an angular momentum and torque. Okay. So a turbine fan in a jet engine has a moment of inertia of 2.5 kilograms meter squared about an axis of rotation. As the turbine starts up, its angular velocity is given by this one. So find the fan's angular momentum as a function of time and find its value at 3.0 seconds. So find the net torque of fan as a function of time and find its value at 3 is equal to 5. Okay. Here, uh, a turbine engine has a moment of inertia. Okay, the turbine starts up. Its angular velocity is given by, so given by 2t. Okay. So find its fan. Okay, so let's start with letter A. Okay, find the fan's angular momentum as function of time. So let's find the angular momentum. So we have here Lz, okay, is equal to I omega z. This is the definition of for a rigid body. So we have 2.5 kilograms uh, meter squared, okay, times the angular 4.0 radians per second cube times t squared. This is the okay. So when t is equal to 3 seconds, when t is equal to 3.0 seconds, we have LZ. uh, LZ is equal to 9,000 kilograms, okay, uh, meter squared per second. Okay, so that is the value at t is equal to seconds. Okay, so find the net torques of the fan as a function of time and find its value. Okay, so the net torque, okay, the net torque is just equal to the rate of change of the angular momentum over dt. So here we have actually uh, 2.5 kilograms per meter squared times 40 radians per second cube times 2t. Okay, that's 2t. So we have 2.5 times 40 times 2. Okay, 2.5 times 40 times 2. So we have 200 and the unit is 200 and the unit is kilograms. So we have 200 kilograms per meter squared and we have per cube times t. Okay, this is the net torque. Okay, when t is equal to 3.0 seconds, so our torque is equal to 600 Newton meter. Okay, so that is how to answer this one using this equation. So let's go now to the angular momentum of a rigid body rotating a symmetry is parallel to the angular velocity is given by in this equation. Okay, that's the direction. Let's go now to the conservation of an angular momentum. So when the net external torque acting in a system is zero, so if the net external torque is zero, then the total angular momentum of the system is zero. Okay. So meaning, so if you have an initial angular momentum, which is moment of inertia 1, uh, omega z, so this is equal to I to omega to z. Okay. So we can prove that, uh, so say for example, the net external torque is equal to 0. Okay. So do we need to prove this one? Okay. That this is actually that if the dl is equal to dt is equal to 0. Okay. So meaning the L is constant. Okay, L is constant. Because suppose that uh, body A exerts a force A on B and the corresponding torque with respect to the whatever the point we choose is torque A on B. So if you have two persons, the net external torque is 0. Okay. So for example, we have two bodies A and B. Okay. So we have two bodies and this body A exert a torque uh, A on B. Okay. Is equal to dl B over dt, and we have the body B exert a torque on B on A, which is equal dl A over dt. Okay. Newton's third law states that if you add these two forces, okay, it will become 0. Okay. Furthermore, if the forces act along the same line, just like in figure 10.8, their lever arms with respect to the chosen axis is equal. Okay, the torques of these two forces are equal and opposite. So if you add this torque, so that the torque A on B is equal to plus the torque B on A is equal to 0. Okay. So we have dl A plus dl B over dt, okay, is equal to 0. If L is equal to LA plus LB, okay, so we have that the dl, so we have here that the angular momentum, if the net external torque is 0, then the angular momentum is conserved or constant, meaning uh, your initial angular momentum is equal to the final angular momentum. So we have here the uh, so we have here a physics professor stands at the center of a frictionless turntable with arms outstretched with 5.0 kilogram dumbbell in each hand. So he is set to rotate about the vertical axis, making one revolution in 2 seconds. So find the angular velocity if he pulls the dumbbells to his stomach. His moment of inertia without the dumbbells is 3.0 kilograms meters per second with arms outstretched 2.2 kilograms meters per second with his hands and at his stomach. So the dumbbells are 1 meter from the axis initially and 2 meter at the 0.20 meter at the end. Okay. So let's use this since this is a conservation of the net external torque is 0. Okay, in this particular, so we use that uh, the momentum I1 may1 is equal to I2 omega 2 z. Okay, so let's use that one. So but in this particular example, we have the I of the moment of inertia of the professor plus the moment of inertia of the professor with the dumbbell. So dumbbell. Okay. So the moment of inertia of what we call this one without a dumbbell is given. So we put this one as I1. So I1, so the initial and the final. Okay. So this is given, which is 3.0 kilogram. But the with the dumbbell, so we have actually 2 times the mass, 5.0 kilograms, okay, times the distance, 1.0 meters squared. So Y2, so we have two masses in the same direction. Uh, 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 the, so we have M1, okay, M2 equal to M1. Okay, we have the same radius, so 2 times this one. The moment of inertia, review it. So we have what we call 13 kilograms meter squared. And our initial velocity, angular velocity, is 1 revolution per 2.0 seconds, which is 0.50 revolution per second. Okay. For I2, okay, for I2 is equal to I, I2, I2 proof, okay, plus katong I dumbbell. So when the dumbbell is being put, his arms is no longer, so dumbbell. So I proof, so without, so 2.2 arms outstretched and arms in the stomach, so 2.2 kilograms per meter squared. So plus 2 times 5.0 kilograms times one this in this time a distance of 0.20 meters squared. Okay, so review the the moment of inertia. Okay, so here, so I2 is actually 2.6 kilograms per meter squared. Okay, so here, the omega 2z, so from this equation, is equal to I1 over I2, okay, omega 1z. So, if you sum up 13.0 kilograms per meter squared over 2.6 kilogram meter squared, okay, cancel, uh, times 0.50 revolution per second. So we have this is equal to 2.5 revolution per second, or around 5 times this omega 1 z. So this is how to calculate this one. Okay. Okay, for the gyroscope and precision, I would like to give you, I would like to redirect you I would like to give you the videos for this discussion and study example 10.13. Okay, so that's all. So the link of the video, I will give the link of the video uh, at the comment section. So so that you can understand the precessing gyroscope or the gyroscopes and precision. So thank you everyone for listening, and this is the end of chapter 10.